So one more example of how we would add or subtract fractions with common denominators. Here we see that we have these negative values. So for instance, my first fraction, negative 23 out of 24, is being subtracted by 13 out of 24. And I could actually reinterpret this a little bit differently, but for now let's just say that my solution, we know, is going to have the common denominator. But what goes in the numerator here are actually values that are negative. So I would associate that negative sign with my terms in the numerator here to actually make the computation. So we get negative 23 minus 13 is going to be negative 36 over 24 like this. Now this isn't simplified, but we could say this would be the result ultimately, right? We could simplify by finding the common factors between 36 and 24. In this case, you could say it would be 6. So 36 is actually the same as 6 times 6. And in the denominator, right, we would get 6 times 4. The common factor here reduces, and I get a fraction like negative 6/4. And in fact, we didn't choose the largest common factor between these two values because 6/4 could itself be reduced, right? So what we should say really is that the common factor that is largest between 36 and 24 is actually 12. So it should have been negative 12 times 3 in this case, and 12 times 2 in the denominator. So really I should have a fraction of negative 3/2 for the solution. So there's my simplified version. Sorry it took so long to get there. So let's move on to the more complicated version. How do I add or subtract fractions that don't have common denominators? This is where students usually falter. So how do we add or subtract terms that are of unlike denominators? Well, we've got to do something called finding the least common denominator. And ultimately what we're going to do is find a multiple of those denominator values and create equivalent fractions such that they will then have the same denominator. So let's practice finding the LCD or LCM as it were. And let me give you an example of what might this problem look like. Let's say I want to add together two fractions 1/6 and 1/9. Going back to my pizza example, myself and James are going to have lunch together using our leftover pizzas, right? Let's say I bought a large pizza that was cut evenly into 6 slices, and he has a slightly different pizza that's cut into 9 equal slices, right? Let's assume that the pizzas started the same size. His pizza is cut into 9 bits, mine's in 6, right? So how can we talk about or explain to each other sort of this proportionality of size, right? There's a difference in one slice of my pizza and one slice of his pizza. And so we've got to find a way to communicate. To create this common denominator allows us to create an equivalent way of stating each of these fractions in a way that we can talk about combining them together with a common denominator, as is the case and is necessary to do so by hand. So looking at the denominator values 6 and 9, I need to find the least common multiple between 6 and 9. There's actually a couple ways to do this. The first way is where we just list the multiples of each term. And whichever value is in common to both lists is going to be our LCD or LCM. So for 6, I could list the multiples. That'd be 6 times 1, 6 times 2, 6 times 3, 6 times 4, and so on. For 9, we could do the same. We could say that's going to be 9 times 1, 9 times 2, 9 times 2. Well, we can actually stop at this point because we reached our first common term, 18. There's another method here as well where we use the factorization of each of these terms to create our LCM. So again, we sort of utilize this sort of list method, except now I'm looking for the prime factors of my two digits. 6, for instance, would break down into 2 times 3. 9 would be 3 times 3, like this. So how do we use this to create the LCD or LCM? Well, I list only once the common prime numbers in each of my lists. So for instance, 6 and 9 both have a common prime of 3. I would list that once. And then I can list the remaining factors 2 and another 3 here to create that common factors. So 3 times 3 is 9, times 2 is 18. Sure enough, I get an LCD of 18. So what do I do with this? Well, ultimately what I'd like to do is create equivalent fractions for each of my two terms that have a denominator of 18. And I do so again by multiplying the original by some constant term over itself. So if I want 1/6 to have a denominator of 18, I would have to multiply 6 times 3 and 1 times 3. So 3/18 is the same as 1/6. And for the second term, I would say that I need to get 9 to be a denominator of 18, so I can multiply it by 2 over 2. So now I have two equivalent fractions that have a common denominator. I can approach the problem now as I did before, where our solution is going to have the common denominator 18, and I add together 3 plus 2 for my result of 5/18. So there are two methods here that I've listed. You can view these in a previous lecture if you want some more examples. So let's try one more of these. I'm asked to add in this example 7/12 plus 5/18. So I'll use the list method here. For 12, the multiples would be 12, 24, 36. 18, I get there pretty quickly, 18 and 36. The result here gives me my LCD that I need. And rewriting each statement here, I want, again, to have that LCD as my new denominator. The question becomes, if I'm going to restate 7/12 as a fraction with something over 36, what is the constant term that I need to multiply by top and bottom number to get there? Well, 12 times 3 would get me to 36, so if I multiply that same constant in the numerator, I get 7 times 3 is 21. For our second fraction, 5/18, well, to get to 36, I had to multiply by 2. So multiplying 18 times 2 gets me to 36, 5 times 2 gets me to 10. And so now I can finish the problem off. My solution is going to have that common denominator. I get 21 plus 10 is 31 out of 36. Now 31 is a prime number, so we can say that this is going to be our simplified fraction, and that is ultimately the answer. So now let's look at using the order of operations to simplify some more complex fractions. Say, for example, you are asked to find the square of 1/2 and then divide that by the second expression, 4 plus 3 to the second. We mentioned last time that you can focus on numerator and denominator separately here before doing that sort of final simplification. So my numerator is 1/2 raised to the second power. The exponentiation here of 1/2 to the second power means take your base, in this case the fraction 1/2, and multiply by itself twice. Well, that's just fraction multiplication, so 1 times 1 in the numerator gives me 1, 2 times 2 in the denominator gives me 4. For my denominator, I have the expression 4 plus 3 squared. I can do the exponentiation first here. I get 4 plus 3 squared, which is 9. Again, the base multiplied by itself twice, so 3 times 3. And I get 4 plus 9 is 13, right? Now, let's remind ourselves this is all being divided, right? So I end up with this weird sort of fraction when I combine sort of my terms here. I end up with 1/4 divided by 13. And I say divided by so that you can be reminded that this is ultimately just another way of sporting the division symbol. So 1/4 divided by the whole number 13. And what we know about division of fractions is that really it's the same as multiplication by the reciprocal. So what's the reciprocal of our whole number? Well, if I put it over 1, it becomes clear that the reciprocal would be 1 over 13. And so ultimately I want to create the multiplication by the reciprocal value here, which we said is 1 over 13. And so numerator values being multiplied, I get 1 here, and I'm about out of room. We get 4 times 3 is 52. So 1 over 52 is my result. So let's try a couple more examples before we wrap up. Here we have a similar setup problem, except now I've got to actually substitute in some value for a variable before using the order of operations to simplify. So imagine I have the expression here, 2x squared times y, and I want to substitute in the following values. X equals 1/4 and y equals negative 2/3. So what does this look like? Well, first things first, I need to make my substitutions. And when I make substitutions, I often use the parentheticals here to sort of isolate the values, right? And it'll look something like this. I've got x squared, so that's 1/4 to the second power, and then times y, so negative 2/3 getting multiplied in there as well. So I'll focus on the exponentiation first. 1/4 squared would be 1/4 times itself twice, so that'd be 1/4 times 1/4. And we still have negative 2/3 here. So focusing again just on this portion, 1/4 times 1/4 would be 1/16. So now we have this operation. And since this is multiplication of 3 different terms, I can do this in several different orders. I'll focus first on just these 2 terms, and then finally we'll multiply by 2. So the fraction multiplication here, I have a negative fraction times a positive fraction. So my result should actually be negative. So 2 gets multiplied by some negative results here. In the numerator, I would have 1 times 2 is 2. In the denominator, I would have 3 times 16 is going to be, let's see, it's 3 times 6 is 8. Carry the 1, we get 48 like this. So when I multiply by 2 here, I'm really multiplying by 2 over 1. And since it's a positive times now a negative fraction, I should get a negative result. I get 2 times 2 is 4 in the numerator over 48, right? So we can simplify this fraction finally to get a solution. The values in the numerator and denominator both have a common factor of 4. 4 divided by 4 is 1. 48 divided by 4 is going to give me 12. So I get negative 1/12 for my solution. All right. Let's try one more example here before we wrap up. Here we're asked to evaluate the following expression, P plus Q divided by R. So we're introducing as our substitution here just integer values. When I make my substitution for P, I get negative 4 plus Q, we're substituting in negative 2, and then dividing by R, which is going to be positive 8 here. So focusing just on the numeric values in the numerator, I get negative 4 plus negative 2 is negative 6 divided by 8. Our common factors between 6 and 8 are 2, so if I divide each by 2, I get, for my result, negative 3/4 for the solution. So fairly simple examples. Go and practice this on your own. There's plenty of examples within the text for you to try out. And we'll see you next time on the next lecture. Who knows what it will be.